Hypothesis testing. Test of significance. A statistical hypothesis is a testable statement, an assumption, about a population parameter. This assumption may or may not be true. The best way to determine whether a statistical hypothesis is true would be to examine the entire population. Since that is often impractical, researchers typically examine a random sample from the population. If sample data are consistent with the statistical hypothesis, the hypothesis is accepted; if not, it is rejected. Types of hypotheses. Hypotheses are of two types: null hypothesis and alternate hypothesis. 1. Null hypothesis. A null hypothesis is a hypothesis of primary interest, which is usually put in a negative language. A testing procedure will lead to the acceptance or rejection of the null hypothesis. A null hypothesis exhausts all information about the phenomena. 2. Alternate hypothesis. An alternate hypothesis is complementary to the null hypothesis. It reflects the direction of further choice of a new null hypothesis should the current A null hypothesis be rejected. For example, if the null hypothesis equals to 100, the alternate hypothesis could be I greater than 100, 2 less than 100, or 3 equal to 100. So, there are three specifications of any hypothesis test, and each of the null hypothesis keeps back some information. Test statistic. A test statistic in a test of hypothesis is a function of sample data whose magnitude determines the acceptance or rejection of the null hypothesis under test. General steps in hypothesis testing. Statisticians follow a formal process to determine whether to accept or reject a null hypothesis, based on sample data. This process is called hypothesis testing. It consists of 4 steps. 1. State the hypotheses. Every hypothesis test requires the analyst to state a null hypothesis and an alternative hypothesis. The hypotheses are stated in such a way that they are mutually exclusive. That is, if one is true, the other must be false, and vice versa. 2. Formulate an analysis plan. The analysis plan describes how to use sample data to accept or reject the null hypothesis. It should specify the following elements. Significance level. Often, researchers choose significance levels equal to 0.01, 0.05, or 0.10, but any value between 0 and 1 can be used. Test method. Typically, the test method involves a test statistic and a sampling distribution. Computed from sample data, the test statistic might be a mean score, proportion, difference between means, difference between proportions, z-score, t-score, chi-square, and so on. Given a test statistic and its sampling distribution, a researcher can assess probabilities associated with the test statistic. If the test statistic probability is less than the significance level, the null hypothesis is rejected. 3. Analyze sample data. Using sample data, perform computations to obtain an observed value, FCL. 4. Interpret the results. If the sample findings are unlikely, given the null hypothesis, the researcher rejects the null hypothesis. Asterisk observed value, FCal critical value, FTAB we accept HO. It means that test statistic lies outside the critical region, i.e. lies inside the region of acceptance, hence we accept HO and conclude that HO is a realistic conjecture. F-cal greater than or equal to F-tab, we reject HO. It means that test statistic lies within the critical region, i.e. lies outside the region of acceptance. Asterisk typically, this involves comparing the p-value to the significance level, and rejecting the null hypothesis when the p-value is less than the significance level, p, and accepting HO when the p-value is greater or equal to the significance level, p greater than or equal to. Errors in hypothesis testing. Two errors are liable to be committed in hypothesis testing. Type I error, when the researcher rejects a null hypothesis that is true. Type II error, when the researcher accepts a false null hypothesis. Convicted acquitted. Innocent type I error no error. Guilty no error type II error. It is impossible to carry out a test without errors, neither is it possible to eliminate errors. What is normally done is to keep the size of type I error at a definite value and minimize size of type II error. Alpha, size of type I error. Beta, size of type II error. Inferential statistics use the probability theory, and that helps to estimate, measure and analyze uncertainties about types I and II errors, which are due to chance effects, sampling error, or what is known as coincidence of random sampling, hence. Results from inferential statistics can be regarded as confirmatory since a probability value is established from the integration of test statistic, degree of freedom, and the level of significance. Critical region, or rejection region, of a test. The critical region, or rejection region, is a set on the real number line such that when the observed value of the statistic falls on that region, the null hypothesis, H0, is rejected. To completely specify the boundary of the critical region or rejection region, knowledge of these concepts is desirable. A. Distribution of the test statistic. B. The sidedness of the test. C. The value of alpha, the significant level, of the test. The sidedness of the test tells us the tail of the distribution of the test statistic where the critical or rejection region lies. The boundary of the critical or rejection region is denoted by C alpha, lower, plus C alpha, upper, plus or minus C alpha slash 2, two-sided. C alpha cuts off an area alpha in the lower tail of the distribution test statistic. H1, mu0 equals 0.05 to the left, lower, tail, single tail. Plus C alpha cuts off an area alpha in the upper tail of the distribution test statistic. H1, mu0 equals 0.05 to the right, upper, tail, single tail. C alpha slash 2 cuts off an area alpha slash 2 in the lower, left, tail, and plus C alpha slash 2 cuts an area alpha slash 2 in the upper, right, tail of the distribution test statistic. H1, is not equal to 0 or mu0, two-tailed. 0.025 to the left, and plus 0.025 to the right. Alpha slash 2 equals 0.05 equals 0.25. 2. Critical region. Reject HO, accept HO, reject HO, critical region, region of acceptance. Degrees of freedom, DF. Degree of freedom in a sample is the number of observations that are free to vary. A parameter which indexes the families of t-distributions and chi-squared distributions. A t-distribution with many df is similar to the standard normal distribution, while one with few df has greater variance. The decision rule. In practice, statisticians describe these decision rules in two ways, with reference to a p-value or with reference to a critical region/region of acceptance. Summary of the approaches. Observed value, fcal critical value, ftab for p greater than or equal to, we accept HO. It means that test statistic lies outside the critical region, i.e. lies inside the region of acceptance, hence we accept the null hypothesis, HO, and conclude that HO is a realistic conjecture. Fcal greater than or equal to ftab for p, we reject HO. It means that TS lies within the critical region, i.e. lies outside the region of acceptance. One sample t-test. A one-sample t-test tests the difference between a sample mean and a known or hypothesized value, the test mean. The test uses the standard deviation of the sample, S, to estimate the population standard deviation. If the difference between the sample mean and the test mean is large relative to the variability of the sample mean, then is unlikely to be equal to the test mean. The one-sample t-test procedure, in essence, determines whether the mean of a single variable differs from a specified constant. It tests the hypothesis that a population has a particular mean value, e.g. 0. HO equals 0 sample mean is equal to a specified constant, i.e. there is no significant difference not significant. High is not equal to 0 sample mean is not equal to a specified constant, two-tailed, there is significant difference high, is not equal to 0 is two-directional, meaning that sample mean can be greater or less than a specified constant high, 0, two-tailed. HO, less than or equal to greater than or equal to 0 sample mean is less than or equal to / greater than or equal to a specified constant high, 0. Sample mean is less than / or greater than a specified constant, one-tailed. A one-sample t-test compares the mean of a single column of numbers against a hypothetical mean you entered. SPSS calculates the t-ratio from this equation, where sampling error, i.e. the expected error due to chance effects present in any sampling situation, equals sample mean, hypothetical population mean. This section explains how to conduct a hypothesis test of a mean, when the following conditions are met. The sampling method is simple random sampling. The sample is drawn from a normal or near normal population. Generally, the sampling distribution will be approximately normally distributed if any of the following conditions apply. The population distribution is normal. The sampling distribution is symmetric, unimodal, without outliers, and the sample size is 15. The sampling distribution is moderately skewed, unimodal, without outliers, and the sample size is between 16 and 40. The sample size is greater than 32, without outliers. This approach consists of 4 steps. 1. State the hypotheses. 2. Formulate an analysis plan. 3. Analyze sample data. And 4. Interpret results. Example 30, two-tailed test. An inventor has developed a new, energy-efficient lawnmower engine. He claims that the engine will run continuously for 5 hours, 300 minutes, on a single gallon of regular gasoline. Suppose a simple random sample of 50 engines is tested. The engines run for an average of 295 minutes, with a standard deviation of 20 minutes. Test the null hypothesis that the mean runtime is 300 minutes against the alternative hypothesis that the mean runtime is not 300 minutes. Use a 0.05 level of significance. Assume that runtimes for the population of engines are normally distributed. Solution. The solution to this problem takes 4 steps. 1. State the hypotheses. 2. Formulate an analysis plan. 3. Analyze sample data. And 4. Interpret results. We work through those steps below. State the hypotheses. The first step is to state the null hypothesis and an alternative hypothesis. Null hypothesis, mu equals 300. Alternative hypothesis, mu is not equal to 300. Note that these hypotheses constitute a two-tailed test. The null hypothesis will be rejected if the sample mean is significantly greater or lower than 300 minutes. Formulate an analysis plan. For this analysis, the significance level is 0.05. The test method is a one-sample t-test. Analyze sample data. Using sample data, we compute the standard error, SE, degrees of freedom, DF, and the t-score test statistic, T. SE equals S/SQRT, N, equals 20/SQRT, 50, equals 20/7.07 equals 2.83. DF equals N, 1 equals 50 to 1 equals 49. T equals, mu, slash SE equals, 295 to 300, slash 2.83 equals 1.77. Where S is the standard deviation of the sample, X is the sample mean, mu is the hypothesized population mean, and N is the sample size. We have a two-tailed test. We will check the critical value, F, tab, of 49 degrees of freedom at 0.025, alpha/2, significance level. F, tab, equals F, dF, alpha/2, equals F, 49.025, equals plus 2.010 and minus 2.010, whereas F, cal, equals 1.770. From the T, distribution table, the point that cuts off an area of 0.025 in the upper tail of the T, distribution is 2.010. Since the T, distribution is symmetrical, the table shows the area cut off in the upper tail area only, but we can obtain appropriate lower tail areas, because of the symmetry. Hence, the point that cuts off an area of 0.025 in the lower tail will be 2.010. Interpret results. We cannot reject the null hypothesis because the observed value of 1.77 falls inside the region of acceptance, as shown above. Observed value, fcal, 1.770, critical value, ftab, 2.010, for p greater than or equal to, we accept HO. Again, this means that TS, 1.770, lies outside the critical region, i.e. lies inside the region of acceptance, hence we accept Ho and conclude that Ho is a realistic conjecture. Note, if fcal greater than or equal to ftab for P, we reject Ho. It means that Ts lies within the critical region, i.e. lies outside the region of acceptance. Chi-square tests. 5.1 Chi-square test, goodness of fit. It is non-parametric test of significance, which attempts to find out if there is a significant difference between the proportions of data actually observed in a study with those proportions expected, i.e. it compares frequency observed against frequency expected. Chi-square test describes the magnitude of variation between theory and observation. Test variable not dichotomous with two categories specified. Chi-square is used when measurement on dependent variable can be categorized in terms of frequencies or number of objects or head count in each category. Measurement takes frequency of say, yes and no, pass and fail, defective and non-defective, low and high, male and female, good and bad, present and absent. Many of our questionnaires adopt these syllables. The frequency of such syllables can be tested using the chi-square. Ho, there is no significant difference between the observed frequency and expected frequency. Example 42. Acme Toy Company prints baseball cards. The company claims that 30% of the cards are rookies, 60% veterans, and 10% are all-stars. The cards are sold in packages of 100. Suppose a randomly selected package of cards has 50 rookies, 45 veterans, and 5 all-stars. Is this consistent with Acme's claim? Use a 0.05 level of significance. Solution. The solution to this problem takes 4 steps. 1. State the hypotheses. 2. Formulate an analysis plan. 3. Analyze sample data. And 4. Interpret results. We work through those steps below. State the hypotheses. The first step is to state the null hypothesis and an alternative hypothesis. Null hypothesis: the proportion of rookies, veterans, and all-stars is 30%, 60%, and 10%, respectively. Alternative hypothesis: at least one of the proportions in the null hypothesis is false. Formulate an analysis plan. For this analysis, the significance level is 0.05. Using sample data, we will conduct a chi-square goodness of fit test of the null hypothesis. Analyze sample data. Applying the chi-square goodness of fit test to sample data, we compute the degrees of freedom, the expected frequency counts, and the chi-square test statistic. Based on the chi-square statistic and the degrees of freedom, we determine the p-value. df equals k, 1 equals 3 to 1 equals 2. ei equals n asterisk pi. e1 equals 100 asterisk 0.30 equals 30. e2 equals 100 asterisk 0.60 equals 60. e3 equals 100 asterisk 0.10 equals 10. Chi2 equals sigma, oi, ei, 2/ei. Chi2 equals 50, 30, 2/30 plus, 45 to 60, 2/60 plus, 5 to 10, 2/10. Chi2 equals 400/30, plus, 225/60, plus 25/10, equals 13.33 plus 3.75 plus 2.50 equals 19.58. Where df is the degrees of freedom, k is the number of levels of the categorical variable, n is the number of observations in the sample, ei is the expected frequency count for level I, oi is the hypothesized frequency count for level I, and chi2 is the chi-square test statistic. Interpret results. Observed value, x2 cal, 19.58, critical value, x2 tab, 5.991, for p, we do not accept HO. And because it is not a realistic conjecture. x2 cal greater than or equal to f tab for p, we reject HO. And conclude that at least one of the proportions in the null hypothesis is false, i.e., there is significant difference the observed frequencies and expected proportions. Two independent samples t-test. The two independent samples t-test, also known as unpaired t-test, is used to compare the means of two independent groups, i.e. to determine if two population means are equal. H0, mu1 equals mu2 or mu1, mu2 equals 0. There is no significant, statistical, difference between the means of the two groups. Means of the two groups are equal. Hi, mu1 is not equal to mu2 or mu1, mu2 is not equal to 0. There is significant, statistical, difference between the means of the two groups. Means of the two groups are not equal. This may indicate that hi, mu1 u2, two-tailed. Ho, there is no significant difference in the unit cost between projects delivered using the DB. Significant difference in the unit cost between projects delivered using the DB contracts and those using the TM form of contracts. Two sample t-tests can be used to answer the following questions. 1 is process 1 equivalent to process 2? 2 is the new process better than the current process? 3 is the new process better than the current process by at least some predetermined threshold amount? 4 are the willingness to accept the same for the two WDs? One-sided t-tests are not as common. In this case, the hypotheses are directional. For example, HO, mu1, mu2 less than or equal to 0, or HO, mu1, mu2 less than or equal to 0, the mean of group 1 is less or equal to the mean of group 2, hi, u1 u2 or hi, mu1, mu2 0, the mean of group 1 is greater than the mean of group 2. HO, u1 greater than or equal to u2 or HO, mu1, mu2 greater than or equal to 0, the mean of group 1 is greater or equal to the mean of group 2, hi, u1 u2 or hi, mu1, mu2 0, the mean of group 1 is less than the mean of group 2. Example 35, one-tailed test, upper tail. The Acme company has developed a new battery. The engineer in charge claims that the new battery will operate continuously for at least 7 minutes longer than the old battery. To test the claim, the company selects a simple random sample of 100 new batteries and 100 old batteries. The old batteries run continuously for 190 minutes with a standard deviation of 20 minutes, the new batteries, 200 minutes with a standard deviation of 40 minutes. Test the engineers claim that the new batteries run at least 7 minutes longer than the old. Use a 0.05 level of significance. Assume that there are no outliers in either sample. Solution. The solution to this problem takes 4 steps. 1. State the hypotheses. 2. Formulate an analysis plan. 3. Analyze sample data. And 4. Interpret results. We work through those steps below. State the hypotheses. The first step is to state the null hypothesis and an alternative hypothesis. Null hypothesis, μ1, μ2 7. Alternative hypothesis, μ1, μ2 7. Note that these hypotheses constitute a one-tailed test. The null hypothesis will be rejected if the mean difference between sample means is significantly lower than 7 minutes. Formulate an analysis plan. For this analysis, the significance level is 0.05. Using sample data, we will conduct a 2-sample t-test of the null hypothesis. Analyze sample data. Using sample data, we compute the standard error, SE, degrees of freedom, DF, and the t-score test statistic, T. SE equals SQRT, S12/N1, plus, S22/N2. SE equals SQRT, 402/100, plus, 202/100 equals SQRT, 16 plus 4, equals 4.472. DF equals N1 plus N2, 2 equals 100 plus 100 equals 200, 2 equals 198. T equals 1, 2, D/SE equals, 200 to 190, 7/4.472 equals 3/4.472 equals 0.67. Where S1 is the standard deviation of sample 1, S2 is the standard deviation of sample 2, N1 is the size of sample 1, N2 is the size of sample 2, X1 is the mean of sample 1, X2 is the mean of sample 2, D is the hypothesized difference between population means, and SE is the standard error. Decide the boundaries of the CR, RR, since high, μ1, μ2 7 and TS is positive, 0.670, the test is an upper-sided test and the boundary of CR or RR lies on the upper tail of the T distribution. Its boundary cuts of an area of 0.05 in the upper tail of the T distribution with 198 degrees of freedom. DF equals 198, and alpha equals 0.05. From the T distribution table, the point that cuts off an area of 0.05 in the upper tail of the T distribution is 1.645. Since the T distribution is symmetrical, the table shows the area cut off in the upper tail area only, but we can obtain appropriate lower tail areas, because of the symmetry. Here we need not mark the lower tail area because the test is an upper tail test. Hence, the point that cuts off an area of 0.01 in the upper tail will be plus 1.645. Interpret results. TS, 0.670, lies outside the critical region, hence we accept HO and conclude that HO, μ7 is a realistic conjecture, as shown above. F, tab, of 198 degrees of freedom at 0.05, significance level. F, tab, equals F, df, alpha, equals F, 198.05, equals 1.645 whereas F, cal, equals 0.670. Observed value, fcal, 0.670, critical value, ftab, 1.645, for p greater than or equal to, we accept HO. It means that TS lies outside the critical region, i.e. lies inside the region of acceptance, hence we cannot reject HO. Thank you.